Good afternoon. Please bear with my voice. It's almost gone now. But it's a great pleasure to launch this distinguished lecture series through the Environmental Energy Technologies Division at Lawrence Berkeley National Lab. As some of you know, we just came out of another event in the morning called the Berkeley India Joint Leadership on Energy and Environment, BIJLE, which was launched this morning. And we decided to keep this back to back because one feeds off the other, and you'll see the impact of that when both events are combined. But this event is the distinguished lecture series we decided to start to bring in the brains and the thinkers, the key thinkers around the world, to LBL to talk about energy and environment. The EETD division has a long history. It started in 1973 with the first energy crisis, and people of that age, the thinkers who are still around, Art Rosenfeld, Bob Budnitz, Mark Levine, and they changed the world in their own ways. And now we are in the different kind of energy crisis. And what we want to do is not only to grow our own Art Rosenfelds, the new ones, but also to bring people from the outside to share some of their thoughts. And it is a tremendous pleasure and honor to have someone like Vinod Khosla to come here and share his thoughts. What an appropriate title, Inventing the Future. So, Vinod.
Thanks. Thank you. My goal today will be to give you sort of more the tools to think about things than give you any specific examples, though some of the examples I use may be contradictory to some of the things you may have heard. That just makes it more fun. So hopefully I'll more challenge your thinking than and give you any specific data. I'm going to go through a lot of slides very quickly. The goal is to give you more an overview than go into depth. I would have loved to do this as a 3-hour seminar interactive, but such is life. So there's a fundamental thing I believe in, that sort of by doing sensible, reasonable things, you don't get anywhere except where you've already been. But there's another side of this. This is very old, a few thousand years old. And this question of precision gets in the way, and in fact, maybe the single biggest handicap we have in reinventing our planet. I'll come back to talking about reinventing our planet, and it's far easier. But the problem I see is all the pundits who have forecasts about everything that won't happen. And so I want to give you an introduction to these pundits. And when I say pundits, I mean all the econometric models, the forecasts, the things you have. I came up with this part of the talk after I spoke right after the head of the International Energy Administration and the head of the McKinsey Global Institute, and I said right after the talk, I was the third speaker up, and I said, everything you heard is, from my point of view, nonsense, not relevant, and something you should ignore. So that's just the basis of where I came up with, because they were essentially extrapolating the past and saying, based on past history and econometric models, this is what the world will be like. So I looked at the numbers. This was in 1985, the forecast for the price of oil. And the actual price was a lot lower. This was a 5-year out forecast. The 10-year out forecast was even more in error. This was in 1990, did the same thing. Forecast and error, 5 years out and 10 years out. You get the idea. Now, when the errors are so large, is there a point in making a forecast? But it actually is worth examining why these forecasts are wrong. So my favorite forecast is the forecast for mobile phones. There were many forecasts. This is one of my favorite ones. AT&T paid multiple millions of dollars, I'm sure, to have McKinsey do the best econometric forecast or the best forecast of what the phone market would be like in the year 2000. This was in 1980. McKinsey forecast under a million phones. There were 109 million phones. And it's fun. I enjoy the fun part of it. But I sort of said, why is it so wrong? And the answer is very simple. And some of you may not remember this was the mobile phone in 1980. So they were using yesterday's technology to forecast the future. The actual phone in the year 2000 was smaller than the handset code on the 1980 phone. How can you reasonably make a forecast 20 years out when you have no idea what the instantiation of that technology will be? And this is a really important lesson to learn because we see this happening over and over again. So my point is, rather than try to predict, use any of these models, because whenever I look at these models and start digging inside, there's some fundamental flaws in their assumptions. So what is the right way to forecast the future? It's to predict it. But predicting it involves some important criteria, and I'll go through these criteria. These are three important criteria. What I find on the other side of the equation, the environmentalists, and I like to say I'm not really an environmentalist. I may share all their goals, but I'm a pragmaticist. I'm looking for the most impact. These are things that matter: relevant cost, relevant scale, and relevant adoption. What does relevant cost mean? Unless it's cheaper than fossil, it won't be adopted in India and China. And any technology that isn't adopted in India and China is not going to be material to climate change. It may make great impact in the marketplace in terms of making money for somebody. A Prius hybrid is a classic example. Irrelevant to the climate change problem. We'll come back to this. And most people say, oh, whoa. For those of you interested, there's a paper on my website called Prius More Greenwash Than Green. And it actually analytically calculates the carbon emissions per mile driven and the dollars per ton of carbon reduced, because those are the only things that matter. For a technology to be material to the climate change problem, it must address at least 80% of the category and cause at least an 80% reduction in carbon in that category. Anything else is immaterial. So it must cause an 80% reduction, but also penetrate 80% of the market. I'll come back to this, but when a hybrid costs $5,000 or $10,000 more, and the world is going to $2,500 cars, it's hard to imagine how it scales and is material. And I'll come back to this issue of, well, everything declines in cost. Not everything declines in cost, and we'll look at how. And the next thing that's important is adoption risk. The world has talked about how efficiency can reduce costs. But the thing we haven't looked at is how we get it adopted. It makes so much economic sense. I mean, every time I look at it, say, boy, great rates of return on an investment in efficiency, we don't do it. It's also the problem with hydrogen. The adoption risk is too high. And so all these things are important. Now, the global climate change problem is actually a simple problem. We make it out to be far more complicated than it is. Remember I said 80% reduction in carbon emissions in 80% of the segment? There's only 4 segments that matter. So Sheryl Crow can talk about using 1 sheet of toilet paper instead of 2. Those are immaterial. I recently read a book by David Bach on sort of 100 ways to impact your carbon footprint. 95 of them are completely immaterial to the scale of the problem. Scale is what matters. Now, if we look at oil, coal, cement, and steel, those 4 things, if we can do an 80% reduction in carbon, we've solved the problem. If we don't do those 4 things, there's nothing else we can do that will be material enough to matter. So let's reduce the problem to replacing those 4. I'll come back to this issue. And efficiency is interesting in it's only a tool to reduce coal and oil consumption. So electric cars, unless there's a black swan. How many people have heard the term black swan? A few terms. I think the book Black Swan was one of the most important books I've read in a decade, because it's the only way we'll change the world. We're not going to get there incrementally. We're going to get there with radical ideas. We weren't going to change the telecom world by incrementally improving ISDN technology. For those of you who remember, the telco world believed that nothing else was needed. And why would anybody need either a computer in a home or more than 100 kilobits in a home ever? So electric cars would only work if there's a black swan in battery technology. What do I mean by that? If you extend lithium-ion chemistry or nickel metal hydride chemistry or lead acid chemistry and say, in the ultimate, everything's reduced to the cost of materials and the fundamental electrochemistry, the science limits, you're getting a 2 to 4x improvement in price performance at best. They are dead-end roads to really penetrating. And the other side of the equation, will ship 1 billion cars on this planet in the next 15 years. This is why something that sells 1 million cars would be a huge product line is irrelevant to the scale of the problem. Most of those billion cars will be very cheap, very low cost, and efficiency doesn't matter. And most of them won't be in the US. So really important that we get some black swan. Now, what's a black swan example? How many people have heard of a battery company called E-Store? Sort of unusual ceramic chemistry. Most people would say not feasible. It may be feasible, may not. We're not investors in it, but I believe something like that is feasible. In sort of, I won't go into it any further. So I won't go through all of these, but let me take some other favorites. Wind and photovoltaics. Photovoltaics projected to grow rapidly, grow 10,000%. Well, if they grow 10,000%, there will be some fraction less than 5% of worldwide electricity. It's the 95% that matters. And so if you're going to make photovoltaics and wind scalable, I believe they're irrelevant to the climate change problem unless we do one thing, which is get storage. So to make them feasible, we need storage technologies, not better wind turbines. We're close enough to the Betz limit on wind turbines. We don't need to do more. I mean, we should do that, but that's not what makes wind scalable. Geothermal is another example. Great technology, completely irrelevant to the scale of the problem unless we do engineered geothermal. So it's the only thing we really should be working on. In fact, engineered geothermal may be the only technology that meets all the criteria to be really scalable. So this is what relevant solutions mean. 80% lower carbon for 1 billion cars. And that includes adoption risk, the risk that people will actually buy it at the price points. It's replacing coal as a power source, not expanding wind and photovoltaics. It's what replaces coal as a power source. I won't go through all of these in the interest of time. And I'll skip our rules of investing. But it's important to realize that we want both manageable and material problems. Geothermal is a great technology, but it's not material. Not material till you get engineered geothermal systems. What's material but not manageable? Behavior change I find unmanageable. Human beings just don't change. We need to sort of kill all the people and invent new people, so it takes 50 years to really do behavioral change. I'm not saying we shouldn't try. We absolutely should. For the incremental hour I spend it on technology, not on behavioral change. Also important to realize that subsidies can't scale. There's not enough money in the world to subsidize energy at any material scale. So we can talk about subsidies and incentives, but we have to reach unsubsidized market competitiveness. We need technology that scales, technology that has short innovation cycles. Nuclear is a great technology. If I invent some great new passive cooling idea for nuclear reactors, if I'm lucky, 2030 will be the first actual deployment. If I invent a solar thermal technology, I can deploy it in the next year and then every 6 months have a new innovation cycle, a new idea tried out in practice. So short innovation cycles. And finally, declining cost with scale. This is another problem with wind. Wind turbines are at the efficiency limit. You're getting costs increase as blade size increases to improve efficiency. But that's really not the material part. The material part in wind is we're using up the best sites. So as we scale, we'll go from class 7 sites to class 6 sites to class 5 and 4 and 3. And so you have a real estate issue which is fixed. So I believe the way to solve this problem is to use technology, which is sort of perfect for this audience. Technology does expand the art of the possible. Today's unimaginable is tomorrow's conventional wisdom. Only 10 years ago, if you said to AT&T long distance calls will be free, and if they are, you'll be out of business, they would have laughed you out of the room. I actually had that conversation. Right? I had the conversation with the media companies on how important Google and the internet would be before Google were invented. Actually, we talked about building a new what was called the New Century Network. Same thing happened with the pharmaceutical companies when they ignored biotechnology. So the title of this talk, To Predict the Future, Invent It, is the only way. I won't spend time on black swan solutions, but they are events with rarity, extreme impact, and only retrospective predictability. And you'll see this happen over and over again in an election that's a surprise the day after. Every pundit predicts exactly why what happened. They can retrofit a model to it, but they didn't do it the day before. The Black Swan book essentially predicted the financial crisis that's happening today. And I find it sort of positive black swans is the way to change the world for the better, and we can expect plenty of negative black swans. And in terms of what all of you are doing, the right strategy is to take more shots on goal, more tries. Just try things. So let me talk about a few what ifs. Let's imagine the world differently. If I said to you, the best way to clean up the air is to build more coal plants, you'd say, you're crazy. What if driving more meant less carbon? I mean, my favorite is all crude oil is produced from biomass. It just takes 1 million years. What if we could reduce it to a few minutes? Every one of those is something we're working on. Now, we might fail, but as I'll tell you later, we might try and fail, but we won't fail to try. And that is the key to let these black swans happen. So before we delve into doing this, what are the key criteria that all of you should be thinking about? Trajectory. What isn't important. What can be is what matters. And that's about inventing the future. It's about adoption risk. And beyond that, there's a few other criteria. Capital formation. If you can't attract capital, You know this in your research. No matter how important it is, if you can't convince other people to fund it, it doesn't go anywhere. And finally, optionality, I'll talk about that. This is a typical curve for a lot of technologies. The cost comes down over time. If this is the cost of a fossil alternative, and if you have a carbon price, this line just moves up. That's how you should think about carbon prices. This is when you need support for a technology. The key question is, you'd like to go faster than that, but how do you tell if it's never going to reach that market competitiveness? This is a judgment call. There's no way to do it any other way. And this is probably the hardest thing we do and look at. And you see curves like this. This is based on data out of Berkeley on the declining cost of various technologies. But not all technology curves are the same. You can have a solar curve, a wind curve, a coal curve. Every technology is in a different port. Important to realize what's cheapest today may not be cheapest tomorrow, so we have to sort of look at where things can be, what the trajectory is. Trajectory matters, and I've seldom seen it really be considered in policy choices. This is the cost of a transistor, various silicon geometries, each one declining cost, but then there's a new generation. And we can see that in solar cells, crystalline silicon, amorphous silicon, thin film. We'll see the same pattern. But that isn't enough. When you look at a technology like solar cells, you might have a cost curve that looks like this, but you may have inputs. Land may open up because we're building more grid to the right locations. Because in biofuels, we're getting larger scale for biomass. You can see curves like this, or they can be going up. In the case of wind, the best wind sites are getting more expensive. And then there's this small matter of construction costs. Right? They generally go up. And the relative proportion of these three costs is what determines the final trajectory. Are we on a declining trajectory, a total increasing cost? And you'll see that this error shows up in a lot of common technology development projects. Photovoltaics, people are going for the lowest cost per kilowatt module. If you do that, your construction costs go up dramatically. So what's very clear today in the marketplace is neither the highest efficiency photovoltaic cell nor the lowest efficiency, lowest cost cell is the lowest total cost. Today, amorphous silicon may be the lowest cost cell, but its construction costs are high enough where it's more expensive than a 12% CAD-TEL cell from First Solar, which is cheaper than an 18% solar crystalline silicon cell from SunPower. So we need to just use these considerations. So I've talked about most of this. Scalability is a key issue. I've talked about wind. There's only so much more we can do in wind turbine design because we are close enough to the Betz limit. We can increase the sites, but good sites are declining. But most importantly, wind is a very erratic source. And if we want to wind scale beyond 10, 15, 20% to 50% and replace coal, storage is the key. So to enable wind, we need to work on storage. Same thing with electric cars. We've talked about this. Natural gas is interesting because T. Boone Pickens has recently proposed natural gas cars. This is a different problem, moderate CO2 reductions. Almost immediately. We know how to get there. In fact, could even retrofit engines. But we can get that 20%, but it doesn't lead to 40, 60, and 80%. So if we put a new infrastructure in place, if our goal is to get to an 80% reduction, it's a dead-end technology because it stops at 20%, doesn't enable the next 20% increments. And we have to keep trajectory in mind. This is the real adoption risk question. This is the Tata Nano. And because of this, there's probably half a dozen other projects at $3,000 or $4,000 cars. So unless a technology, and I actually looked at the volume forecast in 2010 for this car. It's over 1 million units. I looked at the Honda Civic Hybrid, which is not an expensive car that was just introduced in India, and looked at the volume forecast. It's in the thousands. So between 100 to 1,000 times more volume. Nothing you do on the Honda Hybrid will matter to carbon emission averages. This is the problem we need to solve. And it almost certainly will be an ICE engine. I sort of say any technology must pass the Chindia test or meet the Chindia price, the price at which it's cheaper than fossil alternatives, so people will adopt it. There's another adoption risk question, the politics. These are all the paper mills in the United States that are going out of business or have already been shut down. Every one of those dots is 300 to 1,000 jobs. If you have biomass-based fuels, these are all people who can stay in their homes. Adoption risk goes down if you have good dynamics. I've talked about capital formation, short innovation cycles, mitigating technical and market risk quickly, having investor returns, and achieving unsubsidized market competitiveness. These are key criteria for capital formation, and if you achieve these targets, you'll get all the capital in the world. You know, if you look at what's the capital required to replace all the gasoline in this country, it's not much more than what we did per year in the 90s when the telecom internet boom came. The telecom investments were roughly the same size. So it's completely doable. Don't listen to the pundits who talk about trillions of dollars. We can make or invest $1 trillion quite easily if the economics works, because there's that much capital. Keep in mind, we ship $700 billion a year to Saudi Arabia and its allies. That's a year. It's more than sufficient to fund all this if the economics work. The other part of capital formation is you have to have stepping steps for these investor returns. I won't go into this chart. It's on my website in a very old paper I did in 2006. You know, you do, because of corn ethanol, you sort of have some infrastructure being built that encourages the development of cellulosic infrastructure, that'll encourage the development of energy crops, that'll encourage using waste sources, it'll encourage E85 engine up. This kind of stair-step process is absolutely key. If you have to jump from here to here in one step, you will never get there. In fact, my bet is because of ethanol, we'll end up with lots of other fuels that have nothing to do with ethanol, like cellulosic gasoline. No reason it can't be done. In fact, very likely it can be done. So I looked at biofuels, right? And this is where the question of optionality comes in. Those are all the feedstock sources. Those are vegetable oils. They could come from algae, sugars and starches. Algae is down here, and then there's biomass in waste. And all the different technical pathways. The details don't matter. Again, all these are in papers on my website, and lots of different fuels. And I'll tell you, we've seen business plans for almost every one of these fuels. So thinking of biofuels as ethanol is way too narrow. But what's great is, as you see so many options for feedstocks, so many options for technical pathways, and so many options for fuels, we increase our optionality. The probability of technical success goes up. Now, why is technical success important? As you look at feedstock costs, you go down that feedstock list, feedstock costs go down, volume supply goes up, and of course, technical difficulty goes up. Now, these problems, the most solvable problem is the technical difficulty. And so that's what we should try and solve, and we'll solve scalability in the process and cost. We will have low-cost feedstocks and lots of scalability. So we need to be near the bottom. We need to maximize optionality. And this is how I look at hybrids. People always ask me about, so you're negative on hybrids. No, I'm not. I don't think the current chemistries get us to the point where we can penetrate most of 1 billion cars. But I hope we can. It's very simple. If this chart, this is the percentage of power from liquid fuels in the total automotive fleet. So if there's X billion miles driven a year, what percentage of the power comes from liquid fuels? That's in green. And what comes from electric sources? If battery technology moves along the current trajectory, we'll see a curve like this. They'll penetrate, but be a small part of the total over time. However, if battery technology moves quickly and liquid fuel technology moves slowly, we'll see this curve, and liquid fuels will be a small percentage. And this optionality, this battle, is really good for us as a society, and we should encourage both. And this is the best way to look at it. Which curve, this curve, that curve, or something in between, entirely a function of technical progress, which there's no way of predicting. So let's not start extrapolating the past. So the goal is clear: cost, carbon, and scaling trajectories. Capital formation, low adoption risk, and optionality. Those are the key criteria. While doing this, let's avoid the unsensible things. Solar in Germany, I don't think I put my graph in. Germany was 57, or more than 50% of the solar market in like 2005, 2006, last year. They have less solar resource than Alaska. Why are we doing that? The mayor is really proud of solar photovoltaics in Moscone Center. In the best generating time in the summer, San Francisco is a foggy city. It's not very sensible. I sort of said, so why don't you rent the roof of the, not that you shouldn't do photovoltaic panels, just rent the roof of the San Jose Convention Center, put your panels there. Or better sense is still rent some space in the Mojave Desert, and you'll get 50% more output out of the same solar cells. That's important. I won't go into that. Zero energy buildings, major effort, lots of people trying to do it. I don't find it a pretty sensible idea. 2 ways to do zero energy buildings. Now I know some people are going, woo. Putting a solar cell to generate electricity in San Francisco is a bad idea. You should put it in Mojave. Why do we care about one building? It's the total system that matters. And so we ought to optimize the cost. Most people live in coastal areas where energy generation may be more difficult, especially predictable, reliable energy generation. I'll come back to it. Hybrids. Prius, extra $5,000, you reduce half a ton of carbon a year. Now, there's a lot cheaper ways to reduce carbon than spending $5,000. Plant a tree in your backyard. That'll do it. Okay? In fact, McKinsey did a study, and they said the cost of a ton of carbon reduction using hybridization of cars was $90 a ton. Of all the technologies, it was among the most expensive ways to reduce carbon. In fact, they looked at 100, and it was on the extreme right top, most expensive way to reduce carbon. And yet we love the fashion. Same thing with hydrogen. So sensible things. I've said things about biofuels, but it's pretty easy to see how biofuels can be carbon negative or positive, depending upon how we do it. And so I've suggested we have a LEEDs rating for buildings. Why not do a CLAW rating for every biofuel? That's assess its carbon impact, land use impact, its air impact, and its water impact. So if one thing this institute could do is come up with a sensible measurement system for CLAW. Actually, the National Resources Defense Council has taken this up, and they're trying to do some work, but really we need higher quality science and serious science effort to define this standard. We need to do storage. Policy and economic signaling. So in biofuels, I often hear, well, deforestation, with land use, we get deforestation. In the Searchinger model, the science paper says X, Y, and Z. And I've talked often to Tim Searchinger, and we agree 95% of the time. The 5% we don't agree is he says, well, if we're going to have more land use, we should use the 1990s land use change pattern. And I say to him, in 1990, there was no biofuels. So why aren't you actually subtracting that land use trend, that deforestation trend, from what's going on today, and saying any increment above that is caused by biofuels? He didn't do that. In fact, the answer would be you get negative deforestation. But it's worse than that. Instead of using it as a way to sort of reduce biofuels use, why don't we use biofuels as a policy? If we passed a simple rule said we won't import any agricultural products from any country that doesn't meet deforestation reduction targets, we'd use biofuels as a way to stop deforestation. I guarantee you if you ban exports from Brazil, deforestation would stop overnight. Make that a condition of them being allowed. So use economic signals as a policy tool to make the right things happen. Don't extrapolate the past. Make the new future happen. Let me give you, I know we are running short of time, a quick idea of what our technology portfolio looks like. The first thing is the stuff you hear about clean tech, hopefully I've made clear, is not that important. The new green is about main tech, not clean tech. What's main tech? It's about engines. It's about lighting. It's about appliances, about batteries and flow cells. It's about gasoline and jet fuel and diesel and cement and water and glass. This is what the society, the infrastructure of society. It's not about this greeny stuff. It's about what we do every day. And the bulk of what we do every day, not the 5% fringe. So I call this main tech. And I think this is what needs to be 80% lower in carbon, or the carbon productivity has to go up 80%. With that in mind, we divide our investments into 4 areas. We call it the war on coal, the war on oil, the war on efficiency, and new materials. I'll give you a very quick sense of how broad this is. It's not about ethanol. It's not about photovoltaics. It's much broader. In coal, there's lots of technologies, but utility scale solar is probably the most promising in replacing coal, as well as engineered geothermal. In efficiency, there's electrical and mechanical efficiency, lighting, batteries, motors, even the way we build our homes, engines, appliances, pumps, oil. And I'll give you a quick overview of what we are doing in each of these areas. Materials is one of my favorite areas because it's water, which is probably going to be more scarce than oil, and it's about building materials like cement and glass. We have lots of companies in this area. Each one makes for a fascinating story. So I'm going to give you a 15-second tour of each of these, or most of these companies. Engineered geothermal. Instead of relying on geothermal wells to exist, why don't we create them? Altarock is doing that. Osra is doing solar thermal. Instead of doing photovoltaic cell, all they do is use mirrors, which are much cheaper than photovoltaic cell, shine the light into this tube, which directly generates steam, which goes into a 30-year-old steam turbine. Now, 35% efficiency solar cells are hard, 35% efficiency steam turbines are pretty damn cheap. More importantly, the steam can be stored very easily. You can even just pump it underground, and if it's subcritical steam, you've got water, it's got very dense storage, you can easily get to a fraction of the cost of batteries. And so getting to $20 or $30 per kilowatt hour of storage with these technologies becomes very easy, make solar thermal cost competitive with coal. Definitely with coal, it would be cheaper than coal today with a carbon price, but it's getting close enough even without a carbon price, and that's encouraging because this competes with coal. In photovoltaics is not a bare area. SunPower did high efficiency silicon at high cost. First Solar did CadTel, which is low efficiency with low cost. Our focus, Tion, is doing high efficiency with low cost, going directly to thin film multi-junction. So the cost of thin film, the efficiency of multi-junction technologies should easily exceed the efficiency of crystalline silicon. So there's no reason it shouldn't get to 25 or 30% quite easily with the kinds of costs First Solar has. I won't talk much about this. PVT is a company that sort of just, this is actually a pretty dumb idea. A 15% efficient solar cell, this is just your average SunPower or Sharp solar cell, means 85% of the heat, the energy is lost as heat. They collect that 85% and use it effectively. Great Point Energy is doing natural gas from both coal and from biomass. So you get renewable and lower carbon natural gas. PAC's streamline is started in a very simple way. This guy looked at the vortex that forms when your bathtub drains, said, actually took some pictures, froze it, modeled it, just did CFD models. He's now built a tool to modify those vortices and to use them in biomimicry, using biomimicry and computational fluid dynamics for applications in wind turbines and HVAC. So this is one of my favorite. His pumps look like this. This little thing, 9 inches tall. It's only about this tall. I should have brought it. With a 200-watt motor, can mix a 4 million gallon municipal water tank by creating natural vortices. And you can shut the thing off, and an hour later, the vortices are still flowing because they're so energy efficient. You know, right angles isn't exactly how nature intended pumps to work. This is a prefabricated Leeds Platinum home. There's no reason prefabrication has to be ugly. In fact, you can afford to use the best architects because, in fact, you're going to replicate it many times. So this company is sort of, and this home, nothing existed on this site 90 days before this picture was taken. Nothing. Ecomotors doing an opposing piston engine. Lots of advantages to it. This was used in the Junkers bombers in the 1920s. But it was very hard to control timing and all that with chains. Today, with computerization, it's easy. But there's another advantage. When you have opposing pistons, it's a completely balanced engine. So if you have an 8-cylinder engine, you can shut 6 of them off, and you won't vibrate the hell out of the car or ruin its drivability. It'll be perfectly balanced. So they can just switch off modules and get very high efficiency. They also avoid all the heat loss from the head, which is a big source of heat loss in engines. I won't go into all the other things, but they have great scavenging efficiency and a few other things. So they think they can get to twice a Prius's efficiency with a diesel engine. Transonic took a different approach. They said the world thinks there's only 2 types of ignition for engines, either spark ignition or auto ignition. They invented a 3rd type. Now people say, whoa, that can't be. All they did is said gasoline would be great, high efficiency, run at compression ratios of 25. You can't run it there because it self-ignites. So they said we won't mix the fuel in. So they're basically just designing a fuel injector that can be retrofitted into engines. And the fuel injection and the pre-ignition of the fuel happens separate from the compression cycle. And they're seeing about a 50 to 100% improvement in engine efficiency. And all they're doing is changing the injector. In fact, they're using existing diesel engines because they're designed for higher compression ratios. This company is just changing the electronic control turn off cylinders. Now that results in a really unbalanced engine. Hard to do. But if you look at 5,000 RPM and 8 cylinders, that's 40,000 events a minute. And if you real-time balance the vibration, they actually cancel the vibration out by dynamically changing the firing pattern. Don't know whether any of this will work. CO is doing solid electrolyte batteries. Nitash is here. This technology came out of LBL. The basic idea was electrolytes are flammable, and most of the efforts at lithium-ion batteries, like A123, have actually reduced the energy density to increase safety. Why not eliminate the safety problem of flammable liquids by having no liquid electrolyte? Shakti 3 is out of the University of Michigan, thin film batteries, but entirely a computational design approach. I love this because it's a battery being designed on paper. This also is one of my favorites because Firefly is working on lead-acid batteries. And their observation was very simple. In a lead-acid battery, 99% of the atoms of lead are really not on the surface, and they're not participating in the surface chemistry. All the chemistry is surface chemistry. Why don't we eliminate all the atoms that are not taking part in the chemistry? So they build a carbon foam structure, plates, on which they coat the lead. And they've found that they can exceed easily the energy density of nickel metal hydride with the cost of a lead acid. And they should, and that's with changing only one side, the anode and cathode. By doing both sides, they think they can match the energy density, the usable energy density of lithium ion with lead acid batteries and have the cost structure. Kyle's working on blue lasers. This is out of UCSB, Suji Nakamura and his group. We're also working on green lasers, but the most exciting part is with red, green, and blue high efficiency. And these are using different crystal planes than the ones normally used. These are nonpolar and semipolar crystals. But we think we can do, for LED efficiency and direct generation, some amazing things. Topanga took the old HID lamps and put the bulb outside the resonator, and they RF couple it, but because the bulb is completely exposed, you can collect all the light. You don't lose half the light by embedding the bulb inside the resonator. Also, the way they've done it, because it's electrode-less, they can change the gases in there to generate more efficient plasma, and you can have a trade-off whether you want more efficiency in poor color or Range is doing cellulosic biofuels. Again, this is out of order. I apologize. They're using syngas from biomass to produce ethanol. And this is a good example of how the world progresses. So they use syngas from biomass using gasification and then use a catalytic process to convert that into ethanol. Coscata came along and said, Range got the first part right, biomass to gasifier, but we'll biologically convert the syngas into ethanol. That was great. Lanzatech, this is a company in New Zealand, said they're right, but why do we need both hydrogen and carbon monoxide in syngas? There's plenty of carbon monoxide in the flue gases of steel mills and oil refineries and other places. So they designed their bug through the pyruvate pathway to generate its own hydrogen. So it can use flue gases to produce ethanol. And of course, if you have syngas, it can use that too. Mascoma is doing traditional biomass fermentation. They're essentially reducing the enzyme loading by about 80% through some clever thermophilic organisms. I won't go into this. Is Jake Easling's project. Most of you probably know about it. Using the technologies that we use to produce artemisinin for malaria, they were working with a grant from the Gates Foundation, almost the same technology being repurposed to produce diesel because it's just a different chemical factory inside the microbe. LS9 and Chris Somerville was involved in this, as was George Church at the Harvard Medical School. And I love this because people say, well, what's a professor from Harvard Medical School doing producing fuels? But this cross-disciplinary stuff is really, really important. They just focused on the energy production metabolic pathway, optimized it, cut off all the other metabolic pathways, And are starting to see very high energetic yields from various sources of sugar. GEVO was a project out of Caltech. I'm sorry, I'm going very rapidly so I can finish up. That produces butanol. It was the old ABE process, but Francis Arnold essentially optimized to not produce anything else. Here is the process I was talking about. They observed that this is the supply chain today. So if they could take biomass and turn it directly into crude and not turn it into a fuel, they could do it. Now, biomass we know goes to crude oil over a few million years through geothermal conversion. We know pyrolysis is pretty well defined, but it results in very high TAN numbers, acidity, and very high oxygen content. They're developing a different catalytic process to go directly there. This is another one of my favorites. This is a coal power plant, lots of emissions. Calera said, instead of doing CCS, can we convert it into divalent carbonates, which would serve as cement, as building material? So you solve the whole CCS problem with a completely different approach. Why do we want gaseous or liquid sequestration, which is so hard? And thermodynamically, this is a lot more efficient. The only thing you need is a source of calcium ions or magnesium ions. Seawater has plenty of them. And many coal plants are cooled by seawater, so the water is already being drawn. Radical technology that would completely clean up this would be the way to build more coal plants and clean up the air, because the air going into a plant is 380 parts per million carbon dioxide, coming out is 100 parts per million. And we would solve the cement problem. This would be the classic definition. So Keogh and Calera would be the classic definitions of a black swan. Changes every assumption you have. That's why forecasting doesn't work. Dratz is working on bioplastics through, I can't talk too much about the pathways, but this is again very cross-disciplinary. Half the process is microbial conversion, the other half is pure chemistry. This is a professor out of University of Michigan, John Frost. Some of you may know John Frost. So Gaddis, again, I won't go much into it except doing the bioplastics using completely different intermediates. This is a project that did licensed technology out of LBL, electrochromic glass. I won't go into all of it. So let me stop there. Actually, I'll flip to this. This is sort of our view of how life changes. Cement for your home foundations, living homes, prefab leads homes, solar dime, electrochromic windows, fuel for your cars, and more efficient motors, outdoor lighting, better sources of electricity, gas, lighting, water, displays, bioplastics, nylon for your carpets, air conditioners. It's sort of a whole different view of the world. And it's the world that gets me really, really excited, because all of them are feasible. And we do this 100 times over. If we had 100 such portfolios around the world, almost certainly this would be a non-issue. We can, in fact, do this. And in sort of the willingness to fail, to try things that might fail, maybe even will most probably fail, is really the key to success. And I sort of view most of these technologies as ready for replacement. And for this audience, now there's lots to do. And this is just a small list, but thermoelectrics have hardly been worked on. I mean, I suspect with quantum well thermoelectrics, we can get to ZTs above 2, hopefully above 4. And that will completely change so many different areas, including utilizing waste heat. That's sort of sophisticated. I don't know why microwave-based catalysis has been used. You know, if you have a bond you're trying to break, energy at that frequency, resonant frequency, is a lot more effective than blasting the whole damn thing with energy. Or batteries. I've talked about that. But even hydrogen is maybe a great battery if you can have a great round-trip efficiency. My favorite is more efficient cooling. One of the biggest increases in loads is air conditioning worldwide. Happens to happen when the sun's the highest. Why can't we use solar energy, not electrically, but right as thermal heat to produce cooling? There are plenty of thermodynamic cycles we stopped investigating in the 70s. Time to go back to them. So thank you all very much. I know I covered a lot. I could have talked for 2 more hours. This was only 99 out of about 300 slides I have. So I'll take a few questions.
Thank you very much for a provocative, needless to say, provocative lecture. I think this, I'm sure there are a lot of questions out here. So let's just open the...
Hands? Any questions?
Just a couple things that weren't on your lists. What are you doing looking at ultracapacitors as an alternative to batteries? And also, you've been focusing on the cost of the electricity rather than the energy service. And when you look at minimizing the cost of the energy service, combining something like PV and efficiency may allow the cost of electricity to be twice as much because the end-use efficiency investment uses only half as much electricity.
So without commenting on every single part of that, clearly we can combine systems and get more degrees of freedom in how we optimize a system. And I'm sort of, my air conditioning example was one where you use solar energy when at night you might actually resort to electric power, but you have more overall efficiency. So there are plenty of system level optimization opportunities. Ultracapacitors are interesting but too expensive. I think we need something more radical. I think there are opportunities, especially, and this is where some great computational modeling expertise would be really, really valuable. I am actually a huge fan. We are trying some new science experiments that people say will not work, but that's okay. I do look at something like the EUS store battery as not quite a battery and not quite a capacitor. There's some speculation about how something like that might work, where there's not quite a chemistry change which would represent a battery, but it's really hard to predict. Definitely important areas. Yes?
Hi, this is Vinod. We've spoken recently about the need for scale-up capital in the industry, and particularly what happened with range of fuels. Are there any other, what are the other technologies that you see coming online, or ones that you're involved in that are going to need large amounts of scale-up capital?
Oh, all these technologies. You know, solar thermal, if we had the ability to build 2 or 3 generations of plants, would be cheaper than coal within 3 or 4 generations. No question in my mind, especially IGCC coal, even without sequestration. But nobody's willing to put up the 300 million or 500 million it takes to build a plant. And that's risk capital. Same thing with cement. So there's plenty of examples. Yeah.
You mentioned that your goal was to produce a cement which is carbon negative and free. Does your Calera cement from seawater, taking the magnesium from seawater and CO2 from the power plants, achieve that goal?
With a carbon price of $30 or $40 a ton, it's possible to give cement away for free. Aside, I did a calculation on public transportation. Everybody knows public transportation is the best way to be more efficient. Turns out, if you take all the heavy rail passenger miles in the US and divide them by the total electricity used by heavy rail and the total carbon emissions. Carbon emissions on per passenger mile on heavy rail are no different than a regular car. Shocking. You know, I keep asking people to check my calculations because I still don't believe it, but those are the numbers. Being analytical is very key. Yes.
Hi, you didn't mention in particular artificial photosynthetic proposals and using solar to fuel in an inorganic pathway, or maybe PVs that produce hydrogen or things like that would solve the storage problem. and produce. Yeah.
Yeah,
just wanted to
I think they are very promising. In fact, we've recently been looking at a proposal out of Israel. I know Nate Lewis down at Caltech's working on some of those things. I think they're sort of the next generation. I only talked about short-term things, but in fact, the next generation after that is even more promising. So none of this is that important compared to the stuff we will be investing in 5 years from now that's sort of actually taken some serious research. And that research is absolutely key. What all of you do is absolutely key. And in fact, what I'm telling you today is sort of surface stuff compared to what we will be able to do if you focus on it. I mean, people forget that 3 years ago, nobody would talk about any of these things. Yeah.
Could you just give me the 90-second blurb on engineered geothermal? I didn't quite understand exactly.
Well, engineered geothermal is there's heat from magma everywhere on the planet. They're just geothermal wells are where there's also water and steam we can extract. So if you just dig deep enough, fracture the earth at that depth, and people estimate it's between 2 to 5 miles deep. And we know how to dig that deep because we do it all the time in oil and gas. And then create the fractures and circulate water through those fractures, or carbon dioxide, or lots of other things can be circulated. You're creating an artificial geothermal or an engineered geothermal well. That's very scalable because almost everywhere heat exists at some reasonable depth. Not everywhere, but most places. Should be more. Yes.
There's been phenomenal growth in the investment in clean technologies. Do you think there's a bubble, and is it going to burst, or is this different?
Nothing is a bubble when you look at the size of the markets. I don't believe so. And it's important to remember, bubbles are really about stock markets, and I don't deal with stock markets. I mean, people think there was a bubble, internet bubble, and crashed. The stock prices went up and came down. But if you look at internet traffic growth, there was no bubble in that. It has continued to increase linearly every year, including 2001, 2002, 2003. And that's the fundamental of business. It's not stock markets and financial. I mean, that stuff is really game playing, if you want to think about it, built on real infrastructure, real change, and real technology and real innovation.
Well,
Yes.
I think.
You mentioned India and China being essential for relevant adoption. How about for innovation? In your portfolio, do you have any seeing new innovations coming out of that?
Yeah, we're seeing innovation from all sorts of places. The steel mill flue gases into ethanol project came out of New Zealand. Some people were originally working in the pharmaceutical industry down there. The biomass to crude oil project came out of the Netherlands. Couldn't get any funding in Europe. Nobody would take that kind of risk. So there is innovation. We are seeing interesting ideas out of China, out of almost every part of the world. There's bright people everywhere.
Thank you so much. Let me just, before we end, take this opportunity to thank Surabhi Menon, Galen Barbos, Brett Singer, I know you're, and the committee, which did all the groundwork to get Vinod out here. And we're going to get many more speakers, 3 or 4 per year. So again, let's thank Vinod for a very provocative lecture. Thank you very much.
Thank you.